Okay, we're looking at the first page of the 9.6 Convergence Review Worksheet 2. All right, number one. Well, first off, we can note that there's more than one test that could be used to justify convergence for some of the below problems. So I'm just going through the solution that I used for this problems, but there could be more than one test than the ones that is given in the solution here. All right, so if we're trying to determine if a series is converging or diverging, we can always, my suggestion is always test the nth term test for divergence first, since that is usually a quick way to determine if the series will diverge or not. And if that is inconclusive, then we can move on and find other tests. Sometimes going through determining or going through other tests sometimes may be more time consuming, especially not as efficient if we can just go through nth term test first and find a quick answer there. So number one here, limit as n approaches infinity, n squared over n squared minus 1 over n squared plus n. We can go through the nth term test. We see that the degrees match, so we know the limit of this expression will go to 1, and 1 does not equal to 0. So if the rule of sequence does not go to 0, then we know the series must diverge by the nth term test. Okay. Number two, n minus 1 over n squared plus n. Let's go through the nth term test first. Limit as n approaches infinity, the degree in the denominator is higher than the numerator, so we'll go to 0, and if it goes to 0, nth term test is inconclusive. So, but that's just a quick way to test if it's diverging series, and if it's inconclusive, we can then now look at other tests. Now, if I look at the numerator and denominator, the relationship between numerator and denominator is n over n squared, and which is similar to the relationship between 1 over n. Right, the degree in the denominator is 1 higher than the numerator. So we know that 1 over n is a diverging harmonic p-series. So what if we went through limit comparison test, okay, where limit of a sub n over b sub n, and if we evaluate the limit as n approaches infinity of these two ratios, if the result gives us a real number, then we know that it will that by the limit comparison test, this series must also share the same characteristic as this series, which is diverging. So let's just go through this test here. So limits n approaches infinity are a sub n over b sub n, and if we want to evaluate this limit, it's easier if we can reduce and simplify this complex fraction. So I can bring up the 1 over n as n over 1, and then here if I distribute the n through, I get n squared minus n over n squared plus n, and if I evaluate the limit, it will give us 1. So 1 is a real number, which tells us that the limit comparison test is valid. And so limit comparison test says if our result is valid, if it's a real number, then these two series must share the same relationship in terms of what that they're both converging or they're both diverging. In this case, 1 over n diverges, so we know that n minus 1 over n squared plus n must also diverge. Number three, first thing, nth term test. Nth term test will be inconclusive because the limit of this rule of sequence will go to 0. So next up is looking at maybe comparison test, since this is similar to a relationship of 1 over n squared. So if we compare with 1 over n squared, we know that 1 over n squared is greater than 1 over n squared plus n. And because we know 1 over n squared converges, then any series that is less than 1 over n squared must also converge, and we can use direct comparison test there. Number four, we're going to ignore this portion for now. Just look at the n minus 1 over n squared plus n, and we can see that n minus 1 over n squared plus n, limit as n approaches infinity will go to 0. So because the rule of sequence goes to 0, and this is a alternating series, as long as the rule of sequence limit goes to 0, the fact that normally this alone would not be enough to determine convergence. However, because this is an alternating series, every other term is being subtracted out. This is enough to show that the series will converge. So we can say series will converge by alternating series test. And by the way, this is a conditional convergence, not absolute convergence. Number 5, -3 to the n plus 1 over 2 to the 3n. I'm going to try and expand this out here. So I can think of this as -1 times 3 to the n plus 1, and then if I factor out that negative, or if I take out that -1 to the n plus 1, this is really a alternating series here. The rest of it is I can pull out the 3 and then 3 to the n over 8 to the n, because this is 2 cubed n. I can make this 8 to the nth. And if I rewrite it as 3/8 to the nth power, now all of a sudden this begins to look like a geometric series. So a geometric series here, we know the ratio is less than 1 since ratio is 3/8, and because the ratio is less than 1, we know the series will converge. And because this is a geometric series that converges, we can also determine what the infinite sum is. So if I plug in 1 into this expression, I'm going to get -9 over 8, or 9/8. 9/8. So 9/8 is the first term, and then over 1 minus r, the ratio is 3/8. So 9/8 over 11/8 will be 9 over 11. So that's the sum of this geometric converging series. Number 6. Anytime we have expression where the entire expression is raised to the nth power, that's a good indication that root test may be the best fit for this. But first off, nth term test is inconclusive. If we plug in, if we validate limit as n approaches infinity, we're going to get infinity over infinity, and we're not going to be able to quite conclude what's happening using nth term test. So if we do root test here, so limit as n approaches infinity, the nth root of this expression, notice the the exponent and the root will naturally nicely cancel out. So we can just focus on evaluating the limit as n approaches infinity for this expression, the absolute value of this expression, which gives us 3/8, and 3/8 is less than 1. So as long as our ratio, as long as our result is less than 1, we can say that the series will converge by the root test. Okay, number 7, 1 over nth times the square root of natural log of n. Nth term test is inconclusive. So we can see that this maybe is in the form that we can use for integral test. So first off, conditions here. Is the function positive, decreasing, and continuous as n approaches infinity here? So we know the function is positive. So this expression will never be negative. It's decreasing. As n approaches infinity, this value is getting smaller and smaller. And the function is continuous, as from 2 on, there's not going to be any breaks in the graph. So if we think about this in terms of integral test, we can go through u substitution. We can think of the u value as natural log of x. And if we go through, find the derivative, we get 1 over x. dx is dx du. Replace natural log of x with u. Replace dx as x du. The x's cancel out. We're left with integral of u to the -1/2, which becomes u to the 1/2 over 1/2. And then we evaluate the limit as b approaches infinity for this expression. We're going to get 2 square root of natural log of b minus 2 natural log of 2, and we know this will go to infinity. So because the improper integral goes to infinity, we know the series will also diverge by the integral test. Okay, number 8. If we expand this expression out, k factorial, and then we can write this as k plus 2 times k plus 1 times k factorial. The k's will cancel out, and then we're left with exponential over algebraic or polynomial. And by comparative growth test, we know that this series will diverge simply because as n approaches infinity, we have a exponential function that grows at a faster rate than the polynomial, so nth term test will show divergence. So we can just stop there. So that's the nice thing about nth term test. We can sometimes able to get to the answer a lot faster than having to go through other tests. But this can also be found using ratio tests, and because we haven't done ratio tests on this page yet, we'll just go through that practice. So ratio tests, we can find the limit as, in this case, k approaches infinity for a sub n plus 1 divided by a sub n. So a sub n plus 1, we're going to add 1 to each of the k values. So 2 to the k plus 1 times k plus 1 factorial over k plus 3 factorial divided by a sub n. Divided by a sub n is the same thing as multiplying by the reciprocal. And then with the ratio test, we can look to see what we can cancel out here. So 2 to the k will cancel out, remaining with just the 2. K plus 3 factorial and k plus 2 factorial will cancel out, leaving us with just k plus 3. And then k plus 1 factorial and k factorial will leave us with k plus 1. And if we evaluate the limit as k approaches infinity, this will give us 2, and 2 is greater than 1. Now, if the result is not greater than 1, or not less than 1, then we know the series will diverge by ratio test. And this result matches with the nth term test, which shows also divergence. Number 9, k squared over e to the negative k. That's the same thing as k squared over e to the k. E to the k is growing at a faster rate than e in k squared, so nth term test will be inconclusive since this rule of sequence will go to 0. So this is in the form, when we see factorial or exponential functions, usually ratio test is the best fit. So let's do k approaching infinity of a sub n plus 1 divided by a sub n. So a sub n plus 1 is just adding 1 to the k term, so k plus 1 squared over e to the k plus 1 divided by a sub n. Divided by a sub n is the same thing as multiplying by the reciprocal. So next we look to see what we can clean up. So k plus 1 squared, looks like I'm not going to be able to factor anything out or cancel anything out here, so I'm going to expand k plus 1 squared as k squared plus 2k plus 1. E to the k's will cancel out, leaving us with just e to the first power. And k approaching infinity, the degrees will cancel out, leaving us with just 1 over 1 e. So we can think of the e as the coefficient of the k squared. So we're because the degrees match, we look at the coefficient. So coefficient is 1 over e. 1 over e, e is 2.8, which is less than 1. So, or 1 over 2.8 will be less than 1. So therefore, by the ratio test, this series will converge.